I would like to introduce our chief guest and keynote speaker of today's session, Dr. P. Venkateshan sir. He is a professor in Sri Ramachandra University and formerly scientist in ICMR National Institute for Research in Tuberculosis, Chennai. He has an experience of more than 40 years in teaching and research. He has guided more than 45 PhD scholars. His areas of research include disease modeling, HIV/AIDS projections, computational biology, artificial neural networks, support vector machines, genetic algorithms, etc. He has published more than 350 research journals and books. He was awarded Lifetime Achievement Award by the Tamil Nadu Dr. MGR Medical University for the exemplary contribution to the cause of medical education and health research. Eminent Mathematician Award by Biomathematics and Biostatistics Society. Young Scientist Award by Indian Society for Medical Statistics. Renowned Teacher Award by Rotary Club International Chennai. I would like to introduce him to give us some words.
Can I talk?
Yes, sir.
Oh, I was wondering. So, good morning to all of you. So, respected Chief Director, Principal, Head of the Department, Professor Raja, and other faculty members of this great institute, and faculty members from various other departments and various other institutes, and friends and participants. A warm good morning to all of you. Really, it's a pleasure and privilege to be part of this program. And as it was mentioned, that this is the first program that has been organized by a very young department on machine learning and data science. So really, I wish the program all success and hope the department will flourish under the guidance of so many eminent people who are already there and the board. So, because I'm going to give you the first talk, so thanks for the organizers and Professor Raja for inviting me as the first speaker of this one. So really it is a privilege. So as a talk, just so everything is going to be based on data. So I am from the medical field, working for more than 40 years, modeling all other things, starting from genome to proteome to all kind of omics data. So what we are trying to do is, so for the concept of data science, how we can classify the data in general. We are having four or five important classifications. One is the I-dimensional database. So in a medical context, if you take one patient, I can able to get the genes about 6,000 to 15,000 or 20,000 gene information from a single patient. I may have 100 cancer and 100 non-cancer patients at the most, which calls so many billions. So my idea is to find out which are the genes positive for a particular disorder like cancer. So what you are doing in the conventional statistical analysis, so the number of variables should be always less than the cases. So if you are having 1,000 cases with 100 variables, I can do very good analysis. Where the problem is in any high-dimensional data or big data, the number of variables are going to be more than the number of cases. That means all statistical method fails. Here only the concept of machine learning comes. So where in hardcore statistical computing, you have to at least you have to specify the distribution of that particular thing. Here we need not specify. Given the data, we ask the algorithm to generate or capture the distribution from the information to further analysis. So that's the first thing. So that's how the data science has incorporated machine learning as part of the course, and we are doing. The next one is sparse data. For most of the predictions, the data may not be available. Based on the past data, whenever sparsity is there, how to make it. So a lot of machine learning algorithms have emerged in this case, particularly Lasso type of regression, where you are having more than 20,000 variables or 15,000 variables you can put in the regression set, but make all the variables which are not important to what they call the coefficient zero, sparse data. The third one is most of them will be dealing with what they call the sensor data. So you want to have the response of a particular person and a particular drug or any treatment. You may have observation about you want to observe him for 6 months or 1 year, but you will get observation only after 6 months or 8 months. That means you are getting partial information, what you call the censored information. So censored information, if you calculate even the mean will be greater than something, standard deviation will be greater than something. So there is a big branch of what you call survival analysis to take these censored observations into consideration. That's a big field. particularly when it's out generalize the sensor observation thing in high dimensional database. But it's because data is whatever we are having the high dimensional database. So a lot of new algorithms will come on this one. The data was truncated information. The data is going to be truncated. What do you mean by truncated? It is a limitation of the machine we cannot measure. For example, I measure the viral load of HIV patient. The machine can be able to say up to 10 lakhs it can able to be. About 10 lakhs, the information greater than 10 lakhs copies. And similarly, there will be lower limit, less than 500, less than 100, it won't. So it will be less than 100. So it is either truncated on the upper side and the lower side, the observations are not. So that is not the, this one, it is machine limitation. So how to handle this kind of things in data science? So a lot of new algorithms have come, a lot of new machine learning algorithms have been developed on this one. The other important type of data which we are going to talk about and which is going to take center stage is the spatio-temporal data, because most of the disease context, particularly if you're having current COVID or HIV or any of the disease, how to identify the hotspot. So there's going to be a big thing, the GA-based algorithm, where apart from the data, we are having the geographic coordinates, because each point in the Earth can be identified by a unique latitude, longitude. Of course, the Z coordinate is also there when you are going to higher level of buildings. So X, Y, Z maximum you are having, how to analyze these kind of things, particularly in the context of data science, where the conventional methods are not enough to analyze this one, to capture the information. And the last type of data most of the engineers know, the fuzzy information. So if you got information, age 40 years, weight 180, 150 50 kgs and height 150 centimeters, we got very good methods. Whereas you got a young boy, average height, overweight. So that type of information is very common in medical field, and I understand even it is common in most of the other fields. How to convert them into meaningful information? So here only the concept of fuzzy logic and the recent information comes. So the data is not unique, not only the video data or the audio data itself, even the measuring of this one, numerical data, is very difficult in this one. So how to adapt or how to modify or how to develop new methods based on the machine learning, where the conventional statistical and mathematical methods are not sufficient to analyze this kind of data. That is the main field. That's why the data science and the machine learning are, even though machine learning is a part of artificial intelligence, now it has become an independent discipline by itself because of this one. So with this, so I hope this conference will throw a lot of light on this one. It is a very good effort by the department to organize a talk on the data science related approaches, particularly for machine learning based approaches. And I wish the conference all the success, and hope the participants will enjoy this one and try to learn some new things. I think it's an elaborate program for 2 weeks. They have done persons from all the fields. And on my behalf, I wish the conference all success, and I congratulate all the organizing committee, including Professor Raja and the principal and the management, for taking such an initiative. Wish you all the best. Thank you.
Thank you, sir.
Thank you so much for your wonderful words, sir. Now, I would like to invite our coordinator and assistant professor Revati ma'am to give vote of thanks for our inaugural session.
Thank you, Sabita. On behalf of Ishwara Engineering College, the entire fraternity, it is my proud privilege to propose a vote of thanks to those who are directly and indirectly contributing to this 2-week international FDP on Technology Insights on IoT, Artificial Intelligence and Data Science, organizing by Department of Artificial Intelligence and Data Science. At this occasion, I would like to thank our management, Chairman Sir Dr. R. Sivakumar, Director Sir Dr. V. Subaya Bharati, Chief Director Sir Dr. N. Seduraman, Principal Sir Dr. R. S. Kumar, Vice Principal Admin Sir Dr. K. M. Anand Kumar, Vice Principal Academic Sir Dr. V. Ilango, Dean Academic Sir Dr. A. Saravanan, and various heads of the department. And also extend my sincere thanks to our own head of the department, Dr. S. Kanagasubaraja Sir, for his guidance and moral support to enrich our knowledge with respect to industry need. At the outset, I thank our guest of honor and resource person, Dr. P. Venkateshan, Professor, formerly scientist of NIRT Chennai, for taking out of time from his busy schedule and enlightening us with the knowledge. A special thanks to Web Hosting Committee for their unflinching support and coordination. Last but not least, our heartfelt thanks to all the participants for your active participation from various places. Without your support, the event may not reach the grand success. Thank you all. With his warm words and kind message, we'll meet to the day 1 session. Thank you.
Thank you so much, ma'am. I would like to invite Dr. Venkadeshan sir to take over the session. The session is yours, sir.
Okay, thank you. Thank you. Okay, can you able to see the slides?
Yes, sir. No,
Okay.
sir, share your screen, sir.
Screen shared. I'm shared now.
Yes, sir. Screen sharing.
Screen share. Okay. Now it is visible? Yeah.
Yes, sir. Machine learning approaches for statistical modeling.
Yeah. Okay, once again, good morning. Let us start the session. So my talk is going to be mainly on how to, it's going to be an introductory talk. Just I'm going to introduce some of the basic concepts, how it is different fields of the machine learning and a parallel development in statistics, what you call the statistical learning theory has been developed in a non-mathematical way, and try to present some of the results which are from our papers, which are published as an introduction. Is only to motivate people who are not new to the field, and also to give a revision of those persons who are working in the field but other recent developments. So with this introduction, my plan of my talk. So my plan of talk is going to be something like this, just to give some brief introduction, because most of the introduction is given by our speakers already. Then machine learning per se, what it means, how the machine learning, even though it is part of artificial intelligence, how it differs from AI, because AI mainly deals with the modeling of human behavior and other things, where machine learning is not like that. We are not talking about anything on human behavior here. Then what is the statistical learning theory? Because the learning theory is the parallel development in statistical things, how to handle the high dimension large databases. And it basics from statistics and mathematics, particularly the functional analysis. And lastly, I'll try to see some examples from artificial intelligence, support vector machines. And then we'll say database examples, how they are getting better results. Then genetic algorithm, fuzzy logic, and rough set, because that is the order of the day, where from rough set we have moved to soft set, now to the inner set, we are in so many other developments have come. And lastly, the applications, and then we'll try to present one or two applications depending on the task. So the machine learning, what is machine learning? In simple terms, machine learning is concerned with the development of algorithms and techniques that allow computers to learn. Correct? Learning in this context is the process of gaining understanding by constructing models of the observed data with the intention to use them for prediction. So mainly the purpose is going to be on many machine learning algorithms, given the information, past information, how to predict the future. What are the related fields? So artificial intelligence, all of you know, machine learning is a part of, is algorithmic part of artificial intelligence. So whereas the artificial intelligence is smart algorithms, here the learning algorithms are not, as I mentioned earlier, not about human behavior modeling, anything like that. It is more on how to make the machine to learn from the data and the prediction. And all of you know, statistics is inference, making inference from a small sample. Give me a big data, take a small representative sample, and try to make inference. Data mining is a related field where you say that searching through large volumes of data, that is, given a huge volume of data which is not collected scientifically, which is based there, and we'll try to develop algorithms to uncover or discover the hidden pattern in the huge volume of data In other words, most of the scientific discoveries we try to start with an hypothesis. That's how statistics has been taught, or any science. Always start with an hypothesis. We collect information, we try to answer the question, either accept what you call in the terms of whether rejected or not rejected. But data mining is not like that. Everybody sequencing, for example, they're putting like a waste paper box. You have to develop algorithms to generate hypotheses. Then you have to use that is the volume. So there is going to be a large volume of data out of algorithms. So actually computer science, all of you know, because the efficient algorithms are complex models. Basically, we'll be dealing with complex models. Then why to learn? Learning is used when human expertise does not exist. For most of the things that are having even this one, human expertise does not exist. Our humans are unable to explain their expertise. So for example, speech recognition, that's one of this. Because once I'm speaking this one, I start from my belly, it has been filtered various channels, and ultimately what I am, this is a signal I'm observing. Given the signal, I have to identify what is the underlying thing or different stages. And one of the models commonly used is the what you call Hidden-Markov model. No, sir. No. And of course, solution changes in time. Computer network, all of you know the routing problem. So that solution needs to be adapted in a particular case, that is biometrics. So it is easier to write a program that learns to play checkers or the backgammon by self-play rather than converting them the expertise of a master player to the program. So with this introduction, that is we talked about formally what is machine learning. The field of machine learning does not study the process of learning in living organisms, that you have to remember. So, but instead studies the process of learning in abstract. The question is how a machine or a computer can learn specific tasks by following specified learning algorithms. Right? To this end, the machine is shown particular examples of a specific task. The goal is to infer a general rule which can both explain the examples it has seen already and which can generalize to previously unseen new examples. So given the first data, how to predict the future, which is unknown, and most of the time data may not be available for the future. How good your prediction should be, there are a lot of measures. So then already we have said machine learning has roots from artificial intelligence, statistics, and computer science. But now machine learning is established as a separate scientific discipline. As opposed to artificial intelligence, it does not try to explain, generate intelligent behavior. But the goal of machine learning is very modest. So it just wants to discover the mechanism by which very specific tasks can be learned by a computer. And once the output of a formal framework, many of the problems studied in machine learning sounds familiar to statistics, because most of the any prediction problem, an estimation problem, because given everything is database. So most of the problems in machine learning sounds from statistics. However, machine learning looks at those problems with a different focus, that is one with inductive inference and the general ability. So put things in a simple form, what we are trying to do is, statistics are traditionally emphasized on the model that can solve analytically. For example, the generalized linear model, the rich class of model, and generalized additive models, we are having error projection, such a lot of models. To achieve these, both restrictions in the expressive power of the models and the parametric distributions are heavily distributed. So whenever you want to do this, you want to identify what is the underlying distribution, first thing. So any statistic always starts with three things. One is what is the specification, what is identification, and the estimation. These are the core concepts in statistics and heavily depend on assumptions. And we got rich class of literature on this one. The next one is data mining emphasizes very large data storage, integration, retrieval, and analysis, particularly because it is not a structured data. And machine learning seeks to use computationally powerful approaches to learn very complex, non or quasi-parametric models from this area, because it is also modeling, but quasi-parametric. Some of these models are closer to human representation of the problem domain per se. And one of the important things is in machine learning approaches, you need to specify the distribution, the underlying distribution, form of distribution is unknown most of the time, like which you are doing in statistical analysis. And most of you know, because the machine learning, hardcore machine learning, we started with artificial neural network, 1940s, early 40s to even this one. So it is an attempt to model the function of the brain. We will capture partially what is the brain function. And in mathematical terms, what we are trying to do is things which cannot be separated in lower dimension can be easily differentiated in the higher dimension. So from a lower dimension, let us say map to a higher dimension from Rm to Rn, where n is a large thing, and then you use hyperplanes to separate them, because that is a neural network. Support vector means the most important the machine learning algorithm as on date is this one. Even you say medical literature, recent papers, we can able to see about 67% of the articles are only based on support vector. Because the difference between a neural network and support vector means there is a learning problem. Any learning problem is very slow. Whereas support vector machine converts the learning problem into a constant optimization problem using Lagrangian multipliers. So any optimization problem, constraint optimization, very powerful, very powerful. In fact, its roots came from the Hilbert space and Banach space of the mathematical analysis, where it's part of functional analysis. So they are very powerful. The genetic algorithm, all of you know, it is going to be based on the hardcore evolution theory, based on Darwin's theory, what you call. So selection, recombination, and mutation. So you can solve any problem, even because we have general genetic algorithm. The powerful thing is even a model with about 2,000 parameters, we can solve genetic algorithm. So any our conventional optimization problems, problems like linear or nonlinear problems, we go from one point to another point one time at a time. So genetic algorithm generates several solutions simultaneously, try to optimize everything. Then we get a class of data in the last setting. So genetic algorithm is called the what you call universal optimization or near universal optimization algorithm. Decision trees, of course, there we got more than 40 decision trees starting from C to 4.5, C5, etc. Decision trees. Fuzzy logic, all of you know, because it's going to be. And hidden Markov model. See, whenever dealing with high dimension database, particularly we are having, given the signal, we identify the underlying state, the hidden Markov model, the most powerful degree. In fact, more than 70% of the algorithms in data science are based on the hidden Markov model concept, underlying concept is hidden Markov model. What is the difference? So, in a conventional Markov model, we are having a one-to-one correspondence between the observed state and the hidden state. Whereas, in the hidden Markov model, several hidden states can give the same signal, given the signal, how to identify the underlying state. That is hidden Markov model. So, most of the things, given the signal, what could be, because it could have come from any of the several n states, how to identify them. And this is the prediction problems. And hidden Markov model is in the biological context, except RNA modeling, all other things are based on the hidden Markov model. The Markov chain Monte Carlo. It is called as model liberation movement. Why it is called as model liberation movement? Because you can construct a model with, let us say, 500 parameters, or it will be 600 parameters, 1,000 parameters. Now it's very difficult to solve analytically. What we try to do is construct a Markov chain for each of the parameters, allow them to run over a long period of time, where the interdependence and the partial dependence will be removed. You will get the ergodic limit of the stationary distribution. Use our conventional Monte Carlo algorithm to generate samples from these. In that way, indirectly, we are characterizing any complex distribution. We can have properties we can study. Of course, cellular automata, all of you know, and this concept is one of the oldest mathematical concepts. And rough sets, that is a very important thing, because it tries to reduce the number of variables as well as the number of cases. So, in fuzzy, we try to have what you call the boundaries. At least in classical sense, the boundaries fixed, the events are mutually exclusive. In fuzzy, the boundaries fixed, but events are not mutually exclusive, there will be overlap. But even the rough side, even the boundary is not fixed. So, very powerful technique for particularly variable selection, what you call the feature selection. And most of the time, we will be using only jointing. So, whenever you are in high dimensional database, try to run a genetic algorithm, try to select the best subset of variables, and when use gives an input as n is performed better, and fuzzy logic and input, and hidden Markov, most of the biological texture prediction problem, for example, the front end used neural network and back end used hidden Markov model. Of course, MCMC with the AN and everything then. And the ensemble methods, these are the rich class of methods where, apart from bagging and boosting random forest, the most commonly used method, there are another 20 variations have come recently. And so, ensemble means because single classifier may not be able to give a correct prediction. So if you combine several things, what you call just like a thread where we are having different things are blended together. So blending different algorithm, weak algorithm to a strong one, the ensemble methods, and most of the current problems which you are having, we can able to solve it. It's a very powerful technique. So with this introduction, let us go for the statistical learning theory because this is for the data science. Because the statistical learning theory is a framework for machine learning drawing from the field of statistics and functional analysis. So it's a parallel development statistics, particularly for machine learning. This is a measure. The statistical learning theory deals with the problem of finding predictive function based on the data. So ultimately, what we are trying to do in any of the supervised learning prediction problem, given x is and y, given the x is no, I want to find out what is the function relationship between y, the different variable, and the x size, and what function could be able to best approximate the relationship. Correct? Then statistics basically tells the form of f for various things. Where statistical is not bothered about the form of it, how good the prediction is based on this one. It regards certain leverages. Then the deals with the problem of finding predictive function based on the data. There's the statistical learning theory led to successful application of the high-dimensional databases such as computer vision, speech recognition, bioinformatics, etc. The learning problem consists of inferring the function that maps between the input and output, such that the learning function can be used to predict the output from the future inputs. Because data is not already varying. So most of these statistical problems, we have only the estimation, the inference, only on this one. Here the prediction is the finding. And of course, learning theory is a problem finding predictive function based on data. Learning falls into many categories. Most of you know about this one. The supervised learning, where we got dependence, independence of variables concept is there. Unsupervised, based on the similarity, no outcome variable, but based on similarity, we'll group them. Semi-supervised learning, then transfer learning, one of the important things where we don't have we have sparse data, no data, how to make prediction based on the previous thing. Transfer learning is one of the important things that has gained a lot of importance for the past 5 years. Of course, reinforcement, all of you know. From the perspective of statistical learning theory, supervised learning is best understood. Then supervised learning, an algorithm is given for sample that labeled some way useful, some useful way. Supervised learning involves learning from a training data set. Every point in the training is an input-output pair where the input maps to an output. The learning from consists of inferring the function that maps between the input and output in a predictive fashion, such that the learned function can be used to predict output from future input. So that is the main purpose. Algorithms takes the previously labeled samples, use them to induce a classifier. Classifier is a function that assigns label to samples, including the samples that have never been previously seen. That's the prediction. The goal of supervised learning is to optimize some measure of performance, such as minimizing the number of mistakes or errors on any sample. Then statistical modeling. Statistical modeling usually works on number of assumptions because one of the major things is there are a lot of assumptions. If the assumptions are not satisfied, most of the times the statistical inference which are made may not be correct. For instance, you take a simple linear, where the most commonly used model, where any supervised learning theory, linear regression, they said you will have. So if you are having a set of data, you are fixing using this one maximum likelihood method or least square method to estimate the parameters, it becomes statistic. So in machine learning, what you try to do, try the data into some training, most of the database into training, saying other thing, prediction. Then use the training data to fit the model. Then use the already tested data to see how correct it predicts. That's the measure. So that's the only difference. The linear regression between the independent. So what are the assumptions we are making? There is a linear relationship between the dependent and the independent variable. Then homoscedasticity means it's a constant variance. Variance is constant for all things. So mean error, the error sector is mean 0. Then the independent observations are independent. Error is normally distributed for each value of the different variable. Very strong assumptions. This is the most misused technique in data science or in this one. Why? Because now it has been reported that per day more than 10 lakhs regression has been carried out of which only 1 or 2 are useful. In the sense, most of them are not checking the assumption. Given the data, they still try to predict, and this one. And the largest regression comes with one assumption because it is generalized linear model. Where in general linear model, the error structure should be always normally distributed. In generalized linear model, the error structure need not be normal. It could be any of the other distributions, but with one condition, what we call the exponential family. Exponential family. So then it generalizes. Even the non-linear comply with continuous, the segregation of boundary, because that is going to boundary can be very important. Whereas machine learning do assume few of these things, but in general, they spared from most of these assumptions because the assumptions are not there. The biggest advantage is that there might not be any continuity of boundary. So mathematically, we say that this is one of the important conditions. Also, we need not specify the distribution of the dependent or the independent variables in a machine learning algorithm. That's the most advanced thing whenever we're having large databases where we don't know where it comes from. Given the data, I try to capture the underlying pattern, generate the distributions. So that is the. Now to give those, what are the problems? Suppose if data will be always a matrix form, correct? The number of variables conventionally we used to have variables in the column wise and the cases in the row wise, correct? Row wise. But in bioinformatics or biological field, the number of genes will be more than the number of cases. So most of the times the variables will be row wise and cases will be column wise. You should be very careful when you are dealing with this kind of high-dimensional databases. So masterful modeling. So number of cases. Now, in statistical analysis, we say that the number of variables should be always less than the number of cases. Then only we can do a statistical first condition. You suppose we are having 1,000 cases, 100 variables, we can do very good analysis. On the other hand, 100 cases with 1,000 variables, all my statistical methods fail. Correct? So what to do? Either is there any way to reduce the number of variables in some way so that still we can use it, or we have to go for the machine learning. So the basic underlying theorems are the foundations of classical statistics, what you call the central limit theorem, the law of large number, etc., are based on these assumptions. So the n tends to infinity when p is very small, then only most of the theorems come. If it is not there, when I deal with high dimensional data, big data, this assumption is violated. That means I cannot do any meaningful statistical analysis directly by using the existing method. There you have to modify. Yes, there are methods by which you can modify. And other approaches, we can use machine learning approaches to do so. So whenever the number of variables are much more than the dimension, then it is called high dimensional database. So statistical method cannot be done. So one way is how to reduce the number of variables, what you call the computer language called the features. And so whenever p is there, how to change them. There are the extraction methods. Is the variable arrival data use at a latent variable concept to modify the principal component or partially spread method to this one. Or you can have best subset selection method like a genetic algorithm, fuzzy or rough sets. You can have the intelligence database. And big data, the problem is both n and p are large. Both n and p are large. But even almost all big data analytics in today's thing, we always assume n tends to infinity much faster than p, then only we can do meaningful analysis. Theoretically, you have to assume that one. When doing analysis, your basic assumption is even n and p are large, but n tends to infinity much quicker than p, then only we can do it. So these are some of the important limitations you should know before why you are going for machine learning, why you are this one. When we can able to do with a simple method, why you have to go complex method? So this is the other thing, correct? Then I said statistical learning, vast tool of modeling and understanding complex. So statistic tools have been modified. The statistical learning theory in 1960 started and parallel development. In fact, your support vector machine, the most important machine learning algorithm is based on the statistical learning theory, a constant optimization, correct? So recently developed area in statistics, the SL has become very hot topic due to the flood of high dimensional big data, and blends well with the parallel development in machine learning. That is the beauty of this one. So for most of the machine learning approaches, because the database, we don't have any theoretical evidence, but it gives the statistical learning theory, gives the theoretical support for most of the machine learning approaches, whether it is going to be support vector machines or it is going to be kernel-based DNA method, everything. You got everything. So it encompasses many methods such as lasso, the syncage estimates. Because I said no syncage estimates, where you are having a lot of variables in the regression. Those unimportant variables, it compulsory makes the coefficient is 0. And sparse regression, because data is very limited, not available, very few observations are available. Then CART, the classification regression is the most commonly used biology classification in disease tree. Boosting, so bootstrap aggregation, that is going to be there. Then support vector machine, etc. In other words, most of the high-level machine learning algorithms are being based on the statistical learning theory. The statistical learning theory, as I said, it consists of the statistical method and the function analysis, particularly from the mathematics. To give some idea about this one, from 1960 to 80, the revolution in statistics occurred. The Fisher's paradigm, whatever you are doing, the frequency-based analysis that is called Fisher's method, introduced in 1920s and 30s, was replaced by a new one. This paradigm reflects a new answer to the fundamental question: what must one know a priori about unknown functional dependency? Because in all our prediction problems, we have the functional dependency, correct? In order to estimate it on the basis of observation, given the observation, you want to identify the best function, best approximation. What? So in Fisher's paradigm, the conventional statistical method, we must know everything, almost everything. We should know what is the function, what is the properties, all things. The new paradigm holds the restriction of the old one. In other words, if it is enough, limited information, we can able to find the best function. So that is the basic. That is the basic where the machine learning has become so popular, particularly in the data science context, because we got theoretical support for most of the things. Where we used to call even a neural net a black box, it's not black box. I can able to give the theoretical justification how they're related, they can able to do it. So it is to give some kind of idea. Suppose given a set of samples, this is the thing, x1, y1, x2, etc. The question is, what is the best function that approximate that predicts y cap? Good predictor of y for future input, where the data does not exist or not enough. So the learning from data to predict, learning from data to predict well the function where there is no data, that is the prediction. So most of our things, in computer science are in big high dimensional database or big data. We want to predict where data is not available out to this one. So what are the assumptions we are making? There exists a joint probability distribution on the space X plus Y. The training example is sampled independently from these are IID. That is one of the assumptions we are making when you are using. In particular, no assumptions on P. What is the distribution of probability distribution? We are not making any assumption. That is the first thing. The distribution of P is unknown at the time of learning. A non-determinate label due to label noise or overlapping classes. The distribution of P is never fixed. Because in statistics, always the parameter is fixed but unknown. Correct? But the distribution you need not know about this one. Class function approach, bother much about this one. There is a method by which a long function and among the best classifier is one that has got smallest risk because the function from database what you call the empirical risk. So among all possible classifiers in a classification problem, what you call the supervised learning, the classification problem, the best one is the Bayesian classifier because among all the things, because it is the best classifier is the Bayesian classifier. In practice, it's impossible directly to compute Bayesian classifier as underlying probability distribution is unknown. The idea of estimating P does not again usually work. So we call the concept of empirical minimization. So the whole field of machine learning, most of the time, it is based on the empirical minimization. In our database, we don't have any theoretical support, but empirical risk minimization. So at the end of 1960, the theory of empirical risk minimization for pattern recognition problem was constructed. The theory includes a general qualitative theory of generalization depending on the necessary and sufficient condition for consistency of ARM. Then a general quantitative theory that is described by bounds on the probability of future ARM. Of course, these are the things where empirical don't bother much about this one. Only you have to see what is the fundamental result. With the probability approaching to 1, no matter what unknown probability distribution is, given more and more data, the expected error of the function that ARM endorses at each stage eventually approaches the minimum value of the expected. In other words, so whatever may be the distribution, because huge volume of data, you've got more and more data, then it approaches probability 0, that means it's equivalent to a theoretical thing. So that is the basis for most of our data science algorithms and machine learning algorithms. So because data is not a problem, it is a database. So eventually approaches value expected one, the function if and only if f has a finite BC, that is Vapnik dimension. Only something about the function analysis. The kernel methods are more powerful for high-dimensional function. The theory search methods rest on the attractive mathematical properties, rules, and Hilbert space of functions. Okay, these are and the corresponding circumference the Banach space. That do. In other words, we have a theoretical justification to enhance kernel-based methods with function composition. So regularization of all of these representations are dense relatives to uniform norm and parameters such representations are used in fit data. So in other, so with this background, now we'll go for the hardcore thing. So I think we have given we have seen what is machine learning, what is the corresponding development statistics, which is more important for data science and machine learning for this one. And then now we'll see for the hardcore neural network are two important concepts. Now we start with neural network because one of the oldest techniques, still popular, still is got this one, where most of the statistical modeling can be done using the neural network. In fact, a neural network with one hidden layer can be able to approximate more than 95% of the complex functions. Only about 5% of the times we need other functions, correct? So ANN is a great deal, basically biologically inspired, attempts to model capabilities of human brain, generating from previous examples to new cases, abstracting essential characters from noisy data. In statistical perspective, it is prediction and classification. So most of you might have seen this kind of slide. So how to define formally a neural network? Artificial neural networks are massively parallel, adaptive, not adaptive. Adaptive. Adaptation is this one, Darwin's theory. Network for simple non-linear computing elements called the neurons, which are intended to abstract and model some functionality of the human nervous system. Some functionalities, not all functionalities. Even if we can able to capture 5% of the functionality of a brain, that's a big achievement. In an attempt to partially capture, because no AI techniques can able to fully capture the function of the brain or human nervous system, capture some of its computation sense. That's what we are trying to do. So most of the statistical techniques, this one is a generalized linear model. It is nothing but a feed for neural with no hidden layer. Yeah, that's why the feed for neural network one hidden layer. It is equal to the projection first regression is the highest dimension model where it encompasses almost all models such a special case. So that's why I said, neural network with one hidden layer can able to approximate more than 95% of the complex function relationship that is going to be there. Of course, we are having discriminantly everything. We can able to see all the statistical methods can be obtained as a particular case of ANN, most of commonly used values. Then, in terms of linear methods, for this one linear regression, everybody knows. Subset selection, how to select the best subset that is going to be there. And most important thing is the syncage estimates. Already in the last show is the syncage estimator. In other words, whenever you use them, how to sync them, because all in unimportant variables you have to remove syncage. Syncage estimates are one of the important. Then linear methods for classification. The linear basis function, because most of the things, and in terms of piecewise linear function, because whenever a polarity is not there, the piecewise version, particularly its primes, and formerly we used to have Fourier transform. Now wavelet transformations outperform Fourier, all of you know, because most of it is this one. Then local smoothing and kernel regression, because this is the main area. Kernel functions are the ultimate thing. Whenever you want to have a high dimensional, infinite dimension space, you want to reduce to a finite dimension space, the kernel regression, the kernels are very useful. That's why it is very useful in big data and high dimensional data, because our support vector mission based on the kernel functions, correct? Then regularization smoothing primes. Actually, that is already know. We are going to concentrate only on this one, non-linear regression, the artificial neural networks. Then we are going to SVM. These two things we'll try to see and try to give some examples where we are working from our paper. Just we will try to quote some of the calculations. Now, to give a simple idea without going for all formal everything, what is a neural network? So, the neural network is going to be one input layer where you will give the independent variables, age, gender, etc. They are independent variables. There will be corresponding weights, and we are going to map the hidden layer and the output layer. And what we are trying to do is, we are going to, it is nothing but the inner product. Multiply each of the value by corresponding weights and try to get this one, the inner product. Apply certain activation function to make the function either -1 to +1 or 0 to 1 most of the times. Then fix a threshold. Then based on this one, the signal function can able to tell you what are the values. So hidden layer from this one. So if you remove the hidden layer, it becomes a simple logistic regression model, correct? It is a simple logistic regression model. Or put it in the other way, you can thought the ANN as a combination of the statistical logistic models, combination of, because from each input layer, we are going to get the inner product, then you are going to apply the activation function, then we are going to use whether it is going to be above the threshold or communicate as 0 or 1, the next thing. That means it is 0, 1 is going to be the output here for each of the nodes after transformation and using the signal function. So it is a logistic regression. Similarly, you can take any number of things, it's going to be a logistic regression. It's a combination of a logistic regression model. That means it's a single logistic model, the neural network combines number of inputs and number of hidden layers. The only problem is in the neural network problem, all of you know, the number of the input is fixed always because we use it to select it. The number of hidden layers and the number of nodes in each hidden layer is arbitrary, correct? Similarly, the function, the activation function which you are using on the signal vector is going to be fixed by us, correct? It is going to be fixed by us. Now, if you, I said one hidden layer can able to approximate more than 95% of functions, but remember, if you are going to increase, if the classification is not accurate, try to increase the number of nodes in each of the hidden layer, whereas, or we can increase the number of hidden layers. Now, there are a lot of papers which have shown that neural network with one hidden layer with 25 nodes is always is not performing better than a network with two hidden layers with five nodes on each. So, in other words, the number of layers, if you increase, the nodes is going to outperform. That is one of the important things. There are a lot of things, because a lot of learning problem, you have to specify thing, error correction method like back calculation, the famous one, back propagation method. So if I want a case, you are training this one, it does predict as a case. If not case, go and try to adjust the weight until I'm getting a case as a case. That's the learning phase. Once we are having it has learned sufficiently, then we are going to use it as a based on test set. We are going to evaluate the performance of the network. Then once it is there, then for future thing, we are going to use a prediction model. Then I will take one example from our paper publication. The secondary structure prediction is one of the major problems in drug development, particularly in medicine. So there are a lot of algorithms, particularly the secondary structure prediction is going to be 50 to 55. We got more than 20 algorithms, particularly. The earliest one is based on the statistical theory 1955, Passman algorithm, where the prediction accuracy is only about 50-50%. Then we are having the information theory based in 1960. Then we are having latest one. We are having the information theory. Then we are having hidden Markov model based, neural network based, support vector mission based, almost all combination. But all the predictions, so as on date is going to be the correct prediction gives only about 75%. In other words, the structure prediction, because we are going to how the molecule is going to be there, based on this one, we are going to target your molecule to attach in the particular site. Correct? Is the prediction of this one. Given a linear thing, how to make it in a two dimension, where it fits. Similarly, we have to go from 2 dimensions, we have to go to 3 dimensions. Even from the first to the second stage, the second dimension, maximum 75% correct prediction. That is 25% of our molecular structure prediction is not correct. So, and the other important thing, there are secondary structure prediction, there are what you call the alpha helix, the exon, the beta strand, and the loops and coils. approximately we know for human being, it is going to be about 30%, 20%, and they are this way. This is the prior information available. And a random prediction without any algorithm, 40% of the times we can have the prediction. So this is a database. This is the sequence. You take any human cell, you are sequencing it, you will get all our things consists of only the cell consists of the 4-letter, what you call the nucleotide, ACGT. Then you take 3 at a time, it becomes a nucleus, right? The length of the thing is 3.2 billion. And in terms of amino acid, it's going to be approximately 1/3 of this one. So the 20, the 60, any 3, if you take it, it will become one amino acid. Any 3 nucleotides will give one amino acid. That means that in the domain we are going to have 3, 3, 3, and correspondingly we are going to have there we are having 21 amino acids. It is a 1-to-1 map, but it's not an all-to map. You see, in simple terms, it is going to be 20 amino acids plus one top bottom 21. So we have to convert it. Then ultimately, we have to extract what you are having. The data is available. Anybody give the protein database is available. It is available on the NCBI website. Anybody can take for any of the disease. For training set, what we did was we taken the albumin structure without beta strands, because the albumin structures are having only coils and alpha. The beta globally contains of only beta strands and this one without alpha. And these are taken as the training set. The secondary structure already is given free form. That is protein families. It's already available. Anybody can download it. The data is in text format. The first line we are having the amino acid sequence. It is 20 amino acid sequence. A, B is not there, C, etc. Then on the second line we are having the structure will be there, whether it's helix or beta C, structure, loops and coils. So don't bother much about this, except to say that it's a very complicated problem. They now I already said. So use features, write a small program, either it's going to be Java. We used to write modern days in Perl, BioPerl. Now you can write Python or you can have any of this program. So convert this. So there are 5 features. One is the 20 amino acids can be classified into 6 categories. Then the relative frequency of this one we can able to calculate. These are one feature. There are 3. The propensity scores, what is this one? And the evolutionary score, how the over a generation, how it has been changed. The output will be always 1 for alpha helix and 2 for this one and 3. So this is the data file. This data has been converted into a number, because we should convert everything based on this one to this one. Then once you are giving this one, any of the algorithms, so we have developed a new algorithm based on the neural network with this one. So what we get was the results. There are 20 recipes that is given. The training we have taken, normally the 2/3, 1/3 rule we have followed. The DN model, what and DN layer 23 now. The correct class of the training set get about 92% score and tested get about 90%. Where from 75% we can able to increase the accuracy of the new algorithm up to 90% correct prediction. Whereas the conventional algorithm for the same data used the GOIR version 4, that's the most recent and the powerful algorithm among all them. Based on information theory, it is only 72% accuracy. So that is the thing. In other words, there's a lot of work we can able to do it out in the prediction accuracy. Now the next one is the image data. All of you know, because computer science are where the bread and bread is the image data where we are going to do. Now what you are having is self-organized. The self-organized maps are what they call other form of neural networks. What does it mean? It is a clustering technique. It is unsupervised learning, because neural networks can be used for supervised as well as unsupervised. So this is a database where we are having, these are the normals. Benign means it is not cancer, non-cancer, or this one, or beginning cancer, we can say it is going to be non-cancer. These are images, and these are the things. So you convert everything in terms of this one. The SOM can able to identify, because we can, the beauty of this clustering method is the most powerful clustering technique. From each of the things, what is the contribution of each of the, for example, radius texture, we can able to identify. We can able to dock his highest level and because RBG quantification will be there. Similarly, I can able to compound plane attributes. We can able to get in no time to explain all the things. In other words, using SOM for the data, we get about 92%, where it was only about 70% in the other thing. So the SOM based unsupervised classification, we can able to see the clustering 92% of the times malignant of the cluster took there and 90% of the time this one. This is one of the, this is only to say that how a clustering game and unsupervised learning can be done using the self-organized maps. The concept is very simple. From an n-dimensional, i-dimensional space, it tries to project to a 2-dimensional or 1-dimensional hyperplane, and from there you can able to get it out to make that's going to be there. The other generalization for neural networks is Bayesian concept, because Bayesian is very powerful. Whenever you are having previous information, because classical inference, we try to, based on the data, then we'll get some result, we'll compare the results, how it agrees with the others and how it contradicts others. But Bayesian, instead of having this, got a distribution for each node. Each distribution you are having a node. A very powerful tool. Now softwares are available. Lot of softwares are available. That is a very powerful thing. So in other words, the conventional thing, these are the things, we know hidden layer, how the inner product has been obtained, how we are adding this one, the output. And these are the things all of you know for a conventional network. But where a Bayesian network, we are asking the distributions, correct? They are distribution, don't bother much, except this is the procedure which works. So Bayesian neural network, Bayesian to consider all possible parameters in the parameter space, and the implementation is very easy because MCMC algorithm is there, because Mark function multiple algorithm, and gift sampler is the simplest one, and we are having the other important things, very powerful algorithm, because even here you need not assume any distribution, because MCMC algorithm, any measure of any continuous function is okay, because we did not even have a distribution for this one. In 1995, it has been because very powerful algorithm for this one. And convolution network, all of you know, because this is order of the day. The convolution network, one of the most powerful algorithm for deep learning with images and videos. So these layers perform one of the 3 types of operations on the data. One is convolution, other one is pooling, other one is rectified learning unit, or RLE. The convolution puts the input images through a set of convolution files. In other words, in simple terms, what you're trying to do is, in image data, whenever you're giving, in conventional thing, what you have to do, you have to extract the features, either using extraction method like principal component or partial square, where the highly correlated image data, we are having starting from 8 to 864 to 256, more than 10,000, 15,000 variables. We try to use the latent variable concept. For each of the latent variable, the principal component, for example, we try to extract the maximum from the first component, then remaining maximum of the second component, etc. A finite number of 10 to 15 or the most 20 or 40 principal components can be able to capture the information contained in more than 5,000, 10,000 variables. Correct? That is the dimension taken. But instead of doing this one, what a convolution network, give the image itself, construct the network a lot of hidden layers, where each hidden layer try to extract 1 or 2 features, or activate 1 or 2 features from the image, then try, once it has captured maximum number of the features, then use the neural network, the second part of this one too. That is the convolution network, correct? Very powerful. So nowadays, because of this convolution neural network, the deep learning technique, so what we are trying to do, we try to give the image as it is, and may ask the algorithm to capture this one. But there are some dangers, because whatever algorithm you are having, if you are extracting the feature, we are getting this one. A lot of papers have shown that the extracting features or selection, feature selection using genetic algorithm or websites or fuzzy logic or combination of that one outperforms than the neural network, because the feature activation very complicated. Then we'll come to support vector machine. The support vector machine, because he said it is a constraint optimization problem using Lagrangian multipliers. In other words, what you are trying to do is, in the support vector machine, how to be a high dimension. So take the inner product, because it's based on the inner product concept. How to find the product of phi of x into phi of y without explicitly specifying phi. That is called the kernel tree. In other words, so if you are inside a high dimension, let us say infinite dimension input space, how to reduce it to a minimum number? So take the sample of points which are in a particular thing, what you call the borders, or this one. and use them instead of using the entire term points, we'll get the better classification. So there are one concept. One is these are two groups very clearly linearly separable. So we can draw a line how to separate them, just like any least square method. So this is the optimal line where it can able to separate. Here you are having this one. So the distance between the points which separate are the points which lie on the boundaries parallel to this one. These are called support vectors. Support vectors. Machine has been added only to say this, because there are a lot of techniques in mathematics and statistics where it has been added. For example, bootstrap, jackknifing, everything. They are got everything because somebody is named jackknife, so I'll put bootstrap. This kind of concepts are there. The distance between the dashed lines is called the margin. The vector point that constrains the width of the margin is called support vector machine. So we always talk about the maximum width between the two groups. Linearly separable, okay. And even suppose all the points inside the circle are one group, all the points outside the circle are another group. So we cannot separate any linear classifier, we cannot able to do it. Map it to a three-dimensional space. Use hyperplane where all the green points will be there. So the function is going to be pi of x1 to comma is equal to, you will get x1 square, x2 square minus 2 x1 x square. So we are having transformation for this one. Up to 3 dimension we can manage. Even 4 dimension time coordinate. Beyond that is very difficult, very difficult. So the support vector mentioned gives a method by which we can able to do this kind of inner product without explicitly specifying what is pi of x. These are the coordinate functions. Coordinate functions are very powerful, particularly in the context of high dimensional thing, how to reduce it. And most of the time, it will be sigma kernels are going to be radial basis kernels because radial is based on the normal distribution. And all of there is a covering theorem because that is one covering theorem which simply says a complex pattern classification problem cast in a high dimensional space non-linearly is more likely to be linearly separable than the lower dimensional space. That's what we said. Given a lower dimension, map to a higher dimension, then it can be easily separable. Just like a balloon, if you're having blowing back there, then we can able to identify this one. So constructing an optimal hyperplane as a distinct surface to separate examples of two classes is the feature space. Give some simple example because it's a theory. So we want to make a classifier, I want to separate them. So previously we got linear classifier, very good, just we can able to classify it, no problem. But here, these are the things. It's a cases and let us say non-cases, we're going to have this one. How to separate them, So here only, among all the classifiers, the support vector outperforms any other method which you are going to do it because kernel functions. Choose an embedded domain into a high dimensional Euclidean space so that the data samples linearly separable. For the large margin data separating hyperplane, the image of these are prediction. In other words, when the data is separable, finding such hyperplane computationally feasible. I will give a simple example. Suppose these are points. I want to separate them using linear classifier. I cannot, at least I have to do two linear classifier. One linear classifier cannot be able to do it. So what you can do is apply a transformation. X map to higher dimension x square, the function f of x is equal to x comma x square 2 dimension. Then this will become a parabola. Then use one simple thing to separate. This is a very simple example, but we are having the previous data, we are having a complication, so we can able to do it. Then, how can you set up? Because the use algorithm that depends only on the inner product of sample points. Sample points are the marginal support vectors. It is enough you instead of having the high dimensional space. Suppose this is the database. There is a theorem, Mess's theorem. If the matrix is symmetric and positive semi-definite, then is the inner product matrix with respect to some embedding. In other words, you can be able to find it. So you need not use all the points. You take only this one. For example, only the sample points. Suppose you are having inner product of range. The definite embedding is explicitly defined matrix of inner products of range. You take only the inner products. This is a MATLAB figure where separation of kernel function. We can be able to draw these kind of things to make classification. So very flexible because the kernel functions, theoretically very powerful functions and high dimension databases. That's why it is picked up like anything. Just qualitatively I given the expression. Theoretically we are having a lot of things. In the theoretical, this is a lot of what is needed in this area, but this is one thing, correct? So the three contemporary models, so far we have seen Neural network, we are having two things. One is what you call the perceptron neural network, the classification. The radial basis function, it is like second type where the radial basis function, we are having irrespective of dimension of this, we are having always one data layer, only one layer that is based on the kernel function. And these are the finality parameters associated with this one, and support vector mission this one. So these are the functional forms of the risk functional forms of the three models. So what we did in one of our papers, just we used all the models. Logistic model is the binary classification model, which is conventionally used, which is from the generalized linear model class. We have taken a diabetic data set based on this one. So it is going to the spectrum, diabetic spectrum, it is spectral data, where we are having readings from 400 to 4,000 readings of this one spectral. And we applied. So where we said the logistic model, sensitivity is calling a diabetic is a diabetic, specificity is calling a non-diabetic is non-diabetic, correct? And corrective classifying 80%, etc. Where the neural network, both multi-layer perceptron as well as radial basis function, performs better than the logistic regression. But support vector mission, you can see it is all mixed. This is some bromide data, complex data, where a mixture of bromides with other things. We want to separate them. So there also the classification was around 70, but the neural networks. This is one of the published papers where we have, it is about 2,000. So this is in other words, for most of the time, even the neural network model, the support vector mission model, performs better than the linear classification particularly. Now there is another data where you can see the data. The ham 10,000 data set is there. This one data set we are having 10,015 image pixel values, and it has accepted more than 20,000 variables. There are 20,000 variables with the 10,000 cases, correct? The ham 10,000, all of you know the data is thin cancer image data. It is there. The images are there, the feature is there, and you are having. So using genetic algorithm, just we have extracted about how many 783 selected features. Genetic algorithm take the original features, it will be a subset of best resolution. Then and support vector mission among all the classifiers, it performed better. Then among support vector mission, we have various classification. You go for any toolbox of MATLAB or anything, you can able to get all this one. So linear, we couldn't see much difference except in terms of ROC. You go that cubic SVM seems to be, or the fine Gaussian seems to be better. Otherwise, in terms of accuracy, everybody seems to be there. There is some difference in the ROC. And decision tree, similarly, we are having. In other words, remember, even getting 80 or 90% accuracy is very, very good here, because here you're using the number of variables are, we extract the feature, we get about 90% correct classification. It is really very good, because otherwise you cannot be able to do it. Then genetic algorithm, all of you know, because it's one of the important techniques, universal optimization based on this one. You can solve even any of the, even y is equal to ax square plus bx plus c, you can be able to solve it in genetic algorithm. We won't do it, because when the number of solutions are going to be finite by high dimensional space, then it tries to generate several solutions at a time and try to optimize everything simultaneously, and the best subset will be on this one. A very powerful tool, and most of you know genetic algorithm. Those who have studied your course, at least master degree, definitely will be. And the back propagation error correction, because we are having neural network, we are having this error, where genetic algorithm, this one, generalized this one, if you are having the genetic algorithm based AN, the error becomes this one. That's why what you used to do is use genetic algorithm as the first step to select everything. Then you are having ANN come on the back, and then you are getting the error is almost minimal. Where a genetic algorithm, this error rate. Back propagation, it goes something like this, then the error, then it comes down after a sufficient number of cases. Where genetic algorithm from the beginning, we are having the error will be go on decreasing. But combine genetic algorithm with ANN, then we'll get very good. So genetic most, that's why a combination hybrid algorithm, genetic algorithm, ANN, most of the times it performs better than the single algorithm. They are not ensemble method. Remember, this first step you are using is one. Ensembles are different. That will. Then the other fuzzy, all of you know, in a classical set theory, the set is uniquely determined by the elements. In fuzzy set, an element belongs to a degree of relationship. What you call the measure of vagueness, how much we are going to have it. Then rough set theory is expressed in terms of boundary region. It is not based on the partial thing. Fuzzy sets are concerned with vagueness, whereas rough sets are concerned with. We are not discussing the theory of because there is no time to discuss. Only some results will show because the rough set I say the most powerful technique for what you call feature selection or best subset variable selection. Correct. The way concept is a pair of precise concept called lower and upper approximation. Lower approximation concept consists of all objects definitely. In other words, we are having the, I said no, in the classical set theory, the boundary is fixed, the events are fixed, the union of all the events, they are disjoint, you the sample space. Fuzzy logic, the boundary is fixed, but the events are not mutually exclusive, so there will be a lot of overlap, common area will be there. But in rough set, even the boundary is not fixed. So what we are trying to do is, the rough boundary will be there, so you are going to fix two, this one, what you call, precise boundaries, what you call lower bound, upper bound. So those points which are within the lower bound, definitely they belong to the set. Whenever it is above the upper boundary, it is not belong to the set. In between, that's called the rough area, based on certain criteria, it may belong to the set or may not belong to the set, correct? It is something like this. Suppose you are having the points based on the algorithm. So the point, yes, so 1, 6 belongs to the set, and 2, 5, 7, they are not belong to the set, and this one, 3, 4, they may belong to the rough, yes or no. But the concept is very simple. Suppose persons you are having n variables you are taking, where all the variables are same for the 2%, where one person is responding, other person is not responding, or one person is busy, the other person is not. That means these n factors or n variables or n features cannot be able to distinguish a case with a non-case, or cure with a non-cure. That means these features are not so they are. So there are all a lot of concepts, the core concept, dead concept, etc. based on this one. Now our context here is the neural network can be generalized using the neuron. Instead of conventional neuron, use the rough neuron. It gives better results. It gives better results. See, the rough set neuron in 1996 was researched by Fon. Yeah, rough neuron is a pair of usually upper and lower bounds, while the output of the conventional neuron is a single value. So this is going to be there. How this can be? One is using Bayesian concept. You can use the neural network. You can use the convolution part where you can able to the number of hidden layers you can use it. The third one is rough set, the rough neuron. You can incorporate fuzzy also here. You can as well. In other words, these are the general agents which performs better when you're dealing with big data and high dimensional databases. So the rough neural network will be something like this. We are going to process it, processing, then the rough set, the algorithm. Then from there we are going to do it. So there are a lot of technicalities involved. So we try to see how we have used it and how we have got the results. There is one variable. It is most of you might have seen this slide also in some of my presentations. So in other words, there are 60 cases with 720 features. That is, variables are going to be 7,129, 60 cases, correct? 60 cases. The data is available here. Embryo central nervous system, group tumors, little bad. So it is going to be the morphological appearance is controversial, which has 720 features. Now the classification problem, two-way classification problem. What we are having is, so genetic algorithm, total, remember, so many subsets have been 36, 7,000 subsets have been. The best subset for the 7,000 total features are how many? 7,129 feature variables, out of which they get 496 they give the best subset, minimum subset variables. And the classification of using this one, the network, or even using genetic algorithm, the classifier, they give 86% correct classification. The fuzzy, it has given slightly lesser number, 329 features, where it give 90%. The rough set, it has taken only 245 among all the things, but number of evaluation subsets are more. If you go this one, you can able to evaluate. Then 92% on this one. So the fuzzy rough classification, almost 98%. So we are having this one rough genetic algorithm, we are having rough sets, we are having fuzzy rough, we are having all the combinations. So the fuzzy rough set has given you about 98% correct. In other words, Even in extraordinary situations where the number of variables are going to be high dimensional, where conventional method is everything, algorithm of this type, what you call hybrid algorithm of combining 2 or 3, we can able to get very good accuracy in a classification problem, even in the prediction problem. It is only an example. These are our public projects. The tables are promote publications. Similarly, one more data, just we'll see. It is going to be 123 cases and 2,500 variables. These are the references for this one. So what you are having here, genetic algorithm. So it selects about 1,014 variables. How many variables are there here? 2,500 variables. So feature selection, it has given 1,400 variables. The correct classification is going to be 81%, correct? In terms 81%. Rough set, it has given about, it's a slightly less number of variables, 754, but 89 correct classification. Neural network, 734, 91. So the rough neural network, you combine both rough set and neural network, it amounts to about even number of features are only 412 and give about 96.2 accuracy. Very good accuracy because in terms of this one, so the performance measure, correct? So just what I have done is I have given a very brief introduction about this one. Why, what are the machine learning? Why machine learning are important? What are the parallel developments in statistics, particularly the statistical learning theory, in a non-technical way, not this one. How it gives a basis for most of our machine learning algorithms. And data science uses the statistical learning theory based machine learning approach for most of the high-dimensional data and big data analytics. And how even in extraordinary situation where other methods cannot be used or even used fail, we can able to combine this one 90. In certain situations, we have the accuracy said no, the image data still we are having only about 86% current classification, 89, 90. Suppose I want to make it 95% or more classification. What we can do is there are a lot ensemble method. We are having recently about 10 new ensemble methods have been proposed where that gives almost 95% current accuracy. I think that things I think it is too much for you now. Once we are familiar with this one. So with this, I have given a very brief introduction about what is the technique, what is machine learning, what is statistical learning theory, what are the basics, and why I have dealt with neural network and support machine learning because these are the two non-linear methods which are based on this one. And we have gone for other important hybrid methods, and we have not touched the MCMC, we have not touched the other thing because time is not there. So a very brief introduction. With this, I think my time is over. So I want to finish in 1 hour. I am finishing in 1 hour. I thank the organizers for giving an opportunity to share some of my thoughts with you. And it's one of the growing area. And we got a lot of things. What I present is not even 5% of the development that is taken in machine learning and statistical learning theory. There is about 95% there. And so far, not even about 40% of the work has been done. 60% core area remains. There's a lot of area where we can work. And very powerful thing. Now, because of computational power and advancement in information theory and the development in computer memory storage and this one, we can do things which cannot be done about 15, 20 years back. We can able to do it. And a lot of softwares have been there. And free software, but one thing, be careful about the free software because it is not perpetual. So you are going to have, if something goes wrong, you cannot find fault with anybody. But try to check. So with this, I conclude my talk. Thanks for the organizers for inviting me for part of this program as a first speaker. As a first speaker, I want to give a brief introduction about all the topics in machine learning and this one. With this, I conclude my talk. And thanks for your patient listening. Thank you all. Wish you all the best. Bye.
Thank you, sir.
Thank you.
Thank you so much for this wonderful informative session, sir. I would also wish to express our gratitude for providing encouragement and new ideas for this evolving world of machine learning approach to statistical modeling.
Okay, thank you.
And to all the participants, the chat box is open up for your doubts.
And participant side, if you have any doubt, please raise your question. Aarti Devarani ma'am.
So we got our first question.
Yeah.
Shweta asked that other than medical field, where can we use the neural networks?
Everywhere, wherever you are having a classification problem, wherever you have a prediction problem. I have given disease, you can do anything. Defective, non-defective, industrial context. Correct? Anywhere. Because wherever you want a classification, either binary or more than two classification, or a prediction problem, definitely you can use it. All the fields.
Thank you, sir.
Outcome is going to be binary. In medicine, we say this is cured, not cured, responded, not responded, etc. Here, in the industrial defective or non-defective, it is going to be business means whether will get profit or non-profit, whether the business will there will be increase or decrease, or everywhere we are out there. Wherever set of variables, where you want to find this one, you can be able to do it.
Thank you, sir. And our next question is from Bharanidharan. He's asking the clarity on difference between hybrid and ensemble learning.
Oh, hybrid means we are combining two things. First of all, suppose I breed neural network with genetic algorithm. First, I train the genetic algorithm to take the feature, then I give as the input, because you are having 5,000 features. I cannot construct a neural network with 5,000 features, correct? So what you are having using genetic algorithm to reduce the number of features, it gives an input for this one. So similarly, for we are having fuzzy neuro system, neuro-fuzzy system, there are various things where we are having. Whereas ensemble is blending same type of classifiers. Here, no, genetic algorithm is one thing, and this one just a hybrid. Whereas in ensemble, it is like a thread. You know, you are having two or three small threads very weak. You blended them. Just you are going to blend them. They are of the same type of classifiers. We are blending them together so that all three or more weak classified put together will give maximum number of correct classification or increase accuracy.
Thank you, sir. Our next question is, what are the advantages of using CNN over ANN? From Ashwin.
ANN, I think they are not. CNN is the generalization of ANN, correct? So whatever I mean, ANN, artificial neural network is this one. The basic for CNN is ANN. So in ANN, you have to give the input variables. Suppose image data is there. The image, you have to extract the features, you have to give the input variables in the input layer, correct? But whereas in CNN, you are not doing anything, just give the images as an input. Then each image features have been extracted by the CNN, convolution network. It is minimizing your work, right? But in terms of difference between neural networks, the number of hidden layers are more, hundreds, 500,000, depending on our complexity. And most of the image data, video data, just we are giving, because extracting features because at times is difficult. We are making the algorithm to extract each hidden layer. We try to activate one or two or extract one or two features. Where otherwise you have to use in conventional algorithm for image data, you have to extract the features, you have to give as the input. The pixel density, for example, you are having cancer and non-cancer image, then you have to say extract features whether going to be 500 or 600 or it's going to be this one. Normally in the matrix form, the data will be there, and MO64. That's the difference.
Thank you so much, sir. Thank you for making everything crystal clear, sir.
Okay.
And this is participants, please note your reminders. Attendance will be calculated automatically from Cisco WebEx, and feedback form will be posted at the end of every session. FDP materials will be shared at the last day of FDP. 85% attendance is mandatory to get your certificates. And tomorrow's session time is from 10 a.m. to 11 a.m. on the topic Insight of IoT by Dr. Ruzo Tamilarasan, Associate Consultant Petro Technology.
Sabeda,
Yes,
one question posted in the chat box.
Yes, sir. Yes, sir. The question is, can we predict the cognitive level of a student based on their performance in classes and exams using neural networks, sir? More
Yeah,
accurate
yeah.
in ML algorithm.
Yeah, neural network, support vector machines, we have anything, any classifier, you can use it. Definitely, we can do it. In fact, most of the credit cards, whether to give loan or not, they're using the neural network for this one. Based on the past history, everything, they will give the loan, credit card, we can use you or not. You go over most of the banks. The underlying algorithm is neural network.
Thank you, sir.
Thank you.
And any other question from participant side?
Probably overloaded because too many
Okay.
topics covered in this on-prem.
Okay.
Actually, it's only introduction I told you because the people should know these are the things available.
Yes, sir.
Thank
I
you,
would
sir.
like
Yes.
I would like to end the session with a word of thanks. We are really thankful to have Dr. Venkatesan sir today with us. We learned a lot, including usage of neural network, and really thank you for making our base really strong. And thank you so much for enlightening us and taking us to this ML world, sir. I would
Yes,
also, yes, sir.
yes, please continue.
I would also like to thank our participants for making use of this wonderful session. Thank you so much, all.
Thank you. Thanks for your kind words. And really, it is a pleasure to join the students, particularly because that is my aim. I'm really very happy to be part of the program and wish the program all success for future. Thank you.
Thank you, sir.
Thank you.
Thank you, sir. Thank you for the invite.
Thanks. Thank you.
Thank you, sir. Thank you, participants. Stay safe.